Hi everyone, welcome back to Gab-Nic Excelsior Nursing Tutoring Center's video on a reading of the Barron's Review course series. Let's review chemistry, the physical setting. You're welcome to purchase the book and read along or just listen in. So we reached up to section 1.7, reporting measured quantities. I'm going to start here where it says every scientific discipline, including chemistry, is concerned with making measurements. Since no instrument is perfect, a degree of uncertainty is associated with every measurement. In a well-designed experiment, however, the uncertainty of each measurement is reduced to the smallest possible value. Accuracy refers to how well a measurement agrees with an accepted value. For example, if the accepted density of a material is 1,220 grams per cubic decimeter, and a student's measurement is 1,235 grams per cubic decimeter, the difference, 15 grams per decimeter cube, is an indication of the accuracy of the measurement. The smaller the difference, the more accurate is the measurement. Precision. Precision describes how well a measuring device can reproduce a measurement. The limit of a precision depends on the design and construction of the device. No matter how careful we measure, we can never obtain a result more precise than the limit built into our measuring device. A good general rule is that the limit of precision of a measuring device is equal to plus or minus 1/2 of its smallest division. For example, in the following diagram, here's the diagram here. The smallest division of the metric stick is 0.1 meter, and therefore the limit of its precision is plus or minus 0.05 meter. When we read any measurement using this meter stick, we must attach this limit to the measurement. For example, 0.27 plus or minus 0.05 meter. Significant digits, also called significant figures, are the digits that are part of any valid measurement. The number of significant digits is a direct result of the number of divisions the measuring device contains. The following diagram shows a meter stick with no divisions. How should the measurement indicated by the arrow be reported? Here, right here, so there are no numbers, so there's no division. Since there are no divisions, all we know is that the measurement is somewhere between 0 and 1 meter. The best we can do is to make an educated guess based on the position of the arrow. To obtain the best educated guess, we divide the meter stick mentally into 10 divisions and report the measurement as 0.3 meter. This meter stick allows us to measure length to one significant figure. Suppose we now use a meter stick that has been divided into tenths, as shown on the next page, and repeat the measurement. So now this one, which goes from 1 to 10. With this device, we can report the measurement with less uncertainty because we know what the indicated length lies. We know that the indicated length lies between 0.3 and 0.4 meter. Allowing ourselves one educated guess, we will report the length as 0.33 meter. This measurement has two significant digits. The more significant digits a measurement has, the more confidence we have in our ability to reproduce the measurement because only the last digit is in doubt. Measurements that contain zeros can be particularly troublesome. For example, we say that the average distance between Earth and the Moon is 2,308 miles. Do we really know this number to 6 significant digits? If so, we would have measured the distance to the nearest mile. Actually, this measurement contains only 3 significant figures. The distance is being reported to the nearest 1,000 miles. The zeros simply indicate how large the measurement is. To avoid confusion, a number of rules have been established for determining how many significant digits a measurement has. Rules for determining the number of significant digits in a measurement. Number 1, all non-zero numbers are significant. All non-zero numbers are significant. The measurement 2.735 grams has 4 significant figures, 4 significant digits, because there's no zeros. Zeros, this is number 2 now, zeros located between non-zero numbers are also significant. The measurement 1.0285 liters and 202.03 torr each has 5 significant digits. So here we see the numbers right here. So if you count these, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. Okay. Number 3, for numbers greater or equal to 1, zeros located at the end of measurements are significant only if a decimal point is present. The measurement 60 grams or 60 grams has 1 significant digit. In this case, the 0 indicates the size of the number, not its significance. The measurement 60 grams and 60.000 grams, however, have 2 and 5 significant digits respectively. So whenever you see a decimal point, then you start counting the zeros. But without a decimal point, the decimal point, you do not count the zeros. Number 4, the numbers less than 1, leading zeros, are not significant. They merely indicate the size of the number or numbers that follow. Thus, the measurements 0.02 kilogram and 0.020 kilograms and 0.000200 kilograms have 1, 2, and 3 significant digits respectively. The significant digits are indicated in bold letters. So here, right, we have 0.02. So the leading zeros do not matter. Here, 0.020. The leading 2 zeros do not matter. Even with this decimal point, we count after the 0. And the leading zeros, 1, 2, 3, 4, do not matter. We count after the last one and start with a 2, and the ones after it or afterwards matters. Okay, so continuing, it says, using significant digits in calculations. Significant digits are particularly important in calculations, including measured quantities, and it is crucial that the result, excuse me, sorry, we have sirens today. Okay, significant digits are particularly important in calculations involving measured quantities, and it is crucial that the result of a calculation does not imply a greater precision than any of the individual measurements. Significant digits are particularly important in calculations involving measured quantities, and it is crucial that the result of a calculation does not imply a greater precision than any of the individual measurements. Calculators routinely give us answers with 10 digits. It is incorrect to believe, however, that the results of most of our calculations have this many significant digits. Multiplication and division of measurements. When 2 measurements are multiplied or divided, the answer should be contained as many significant digits as the less. So when 2 measurements are multiplied or divided, the answer should contain as many significant digits as the less precise measurement. For example, If the measurement 2.3 centimeters, 2 significant digits, is multiplied by 7.45 centimeters, 3 significant digits, the answer must contain only 2 significant digits. So 2.3 centimeters times 7.45 centimeters equal 17.1345 centimeters, which equals 17 centimeters cubed, right? So if you try yourself, you will find that if you divide the following measurements and express the result to the correct number of significant figures, 6.443 grams divided by 8.81 liters, the answer will be 0.723 grams per liter. Okay, so the next thing is in addition and subtraction of measurements. When two measurements are added or subtracted, the answer should contain as many decimal places as the measurement with the smaller number of decimal places. For example, when 8.11 liters, which has 2 decimal places, and 2.376 liters, which has 3 decimal places, are added together, the answer must be taken only to the second decimal place. So 8.11 liters plus 2.467 liters equals 10.586 liters, which truly equals 10.59 liters. And when you try this yourself, it says add the following measurements and express the result to the correct number of significant figures. 2.46.2.3 milliliters, 79.91 milliliters, 8786.268 milliliters. The answer to all of this is 9112.38 milliliters. Note if counted numbers such as 6 atoms are defined numbers or defined numbers such as 273.16 kilograms are used in any calculations, they are treated as though they have an infinite number of significant digits or decimal places. Next, we go to rounding a number. Suppose we have a measurement with 5 significant figures. If we wished to express it to 3 significant figures, we would need to round this measurement. We round a measurement by looking 1 digit beyond the precision we need. So when we round a measurement by looking 1 digit beyond the precision we need. If the digit is less than 5, we do not change the value of the preceding digit. If it is 5 or greater, we raise the preceding digit by 1. For example, if our measurement was 127.36 grams and we wanted to round it to 3 significant figures, we would first examine the 4th digit. Since 3 is less than 5, we would leave the 3rd digit, 7, unchanged, and the rounded measurement would be 127 grams expressed to 3 significant figures. If, however, we wish to round the measurement 127.36 grams to 4 significant figures, we would need to examine the 5th digit. Since 6 is greater than 5, we would raise the preceding digit, 3, by 1. Expressed to 4 significant figures, this measurement will be 127.4 grams. If you try this yourself and you round each of the following measurements to 3 significant figures, A, you would have 903.04, 903.04. The result for that, rounded to 3 significant figures, is 903, because the 0 after the 3 is less than 5. The next one, 298.9 298.86 kilograms, 298.86 kilograms, when rounded to the third significant figure, is 299 kilograms.